Welcome to the 10th show this season. We have Ivan, David, Chris, Yannick, Evan, and myself. And we are trying to, again, do 3 or 4 problems, right? And the first question will be, what? What do you want to do, Ivan? You are going to start with a poll or show them the problem, or what do you want to do?
I think I should show the problem first
Okay.
and let them read the problem.
Can everybody see that? Is that the main screen? Okay. So find the number of 7 tuples of positive integers a, b, c, d, e, f, g that satisfy the following system of equation. A, B, C is 70, C, D is 71, C, F, G is 72.
EFG.
E, F, G.
Yes, and I'm launching the poll where this problem was proposed. So some people might recognize it. Is it a recent one?
Yep.
It's a recent one. That's why Samuel recognized it. He is a librarian of Amy questions right now. You know, that's his job. Remember all those problems. He doesn't know, he might not know how to solve them, but he remembers.
I think you just gave it away.
Yeah.
Oh well.
Okay. It doesn't matter. Okay, we're gonna end the poll here. So yeah, you see Amy wins. Yeah, and let's talk about it. Interesting condition.
So the author is Chris, right?
Yes, it's me. So there's a little bit of backstory as to the genesis of this problem. We were asked when I was on the Amy editorial board back in 2018. They said we have too many problems that are on like the medium end and the 6 through 10 and the 11 through 15. So we were asked to write some problems for the 1 through 5 slots, and I ended up writing this one and a number of other ones on the plane ride to the meeting. One thing about me is a lot of my problems are born on airplanes. I'm sort of confined in a short space and tight space and can't really do much of anything else. And because this was for the 2019 Amy, originally the right-hand sides were 18, 19, and 20. But then the answer was a lot smaller, and so people were concerned that it would be too guessable. So they made them 3 larger consecutive numbers. So someone wrote 71 isn't it prime?
Well, we can easily check.
It's not divisible by 2, 3, and 5, so it must be a prime, right?
Yep.
Close enough.
That's how you check if it's a prime anyway.
So this is the key. You start from here, from a prime, right? So we immediately know that CDE is what? It's 1, 1, 71 in some order, right?
Yeah.
Okay. So then we can follow the logic. David, what do you think we get?
Well, I mean, you know that C is in the first 2 equations, so C divides both 70 and 71. So that means that C divides their GCD, or their difference, rather, in this case. So C divides 1, therefore C equals 1.
And the same way, E divides 72, so E must be 1 and D must be 71. Okay. So let's see, once we get here, we probably do what? See what's left to find.
So you rewrite a new system, right? Yeah, 70. This one you can throw away.
70, not 7.
Sorry?
Yeah.
Okay. So this is where Chris started his problem on the plane. I don't know. And what are these ordered? What kind of integers? Just any, right?
Well, it says seven tuples and there's parentheses. So in general, with n tuples, you should assume order, especially when there's parentheses rather than curly braces.
Yeah. So now it becomes counting how many divisors do you have, right?
Yes.
So I just want to make one challenge for next few years in Amy. There will be one exam. We do not ask them about anything about how many factors a number has.
How do you write number theory problems if you don't ask people about how many factors something has?
Like the one you did last time, you asked for them inverse.
Oh, that's fair.
So we need what? We need to know prime factorization to talk about divisors. So 70 has how many? 8 divisors? And 72 has 3 plus 1, 2 plus 1, 12 divisors, right?
Then you are good, right?
I want to push the paper a little bit up. Yeah.
So what are the possible variations, Chris, you think about if you rewrite this question?
Right. So after the test is given, I sometimes talk to students or look at online forums or what have you, and some people said, "Oh, this is too easy for an Amy problem." I want to challenge the audience, though, that when you see a problem that seems too easy, the challenge is not mathematical as much as imaginative. Like, think about what might be a more interesting, harder question. So initially, the last equation was EFA equals 72. That is, there was sort of a cyclicity. Any two equations shared exactly one variable in common. So that's a little variation. And don't, if you're listening to this, don't post answers right away because I don't want to spoil surprises for people. No spoilers here. What if we removed the adjective positive? What if we took away that constraint? Then it's a little bit of a different question. What else?
Well, another thing I can think about is this 70 or 72. If you make one of them a perfect square, you could twist the problem a little bit, so they have to worry about one over counting. Is it? Yep. If it's not ordered or something, right?
Sure.
Or like Sam was making a comment, what if you don't give them any prime? Then they have much more cases to worry about.
Yep.
Can you come up with a general formula for, let's say, replace 70, 71, 72 with, like, let's say M, N, and P? It might be possible to come up with some formula in terms of, you might have to like sum or all divisors or something like that, but you could probably do that. And then maybe that would, I don't know, you could try doing some things with that. I don't know.
I mean, generally, you just want to consider each prime factor separately, right? Like, I guess the most complicated case is where like all of them are like, say, powers of 2, and then it becomes like, I don't know, placing things around a triangle, and you give them like how many rocks are on each side and how many. I'm thinking of the EFA case, but yeah, like.
Yeah. So the 20th century mathematician Polya said that if you, I'm paraphrasing this, but if you have a hard problem that you don't know how to solve, then there is some easier problem that's related to it, and so find it. And so my challenge here is, if you think that this is a very easy problem, which that was kind of the point of it, was to make it pretty straightforward, approachable. As we've discussed, a lot of it's just logic. You sort of stare at this and you say, well, 71's a prime. And then you look at the common things between equations. There's a common factor of C, common factor of E. So if that sort of is boring and not very interesting, it's sort of the reverse of Polya's principle. Look for a more challenging problem. Look for a more interesting question. Is kind of, and keep in mind that the Amy, there's a broad audience of people that take the Amy. So there are people that they've never seen anything quite like this before. But yeah, there's lots of things.
You didn't have to make it a prime because
sure,
these two numbers are co-prime, which means C must be 1.
Right.
So C is always 1. E is always 1 because these two are co-prime. So D will be this big number. It could have lots of divisors.
Right. Yep.
Okay, I think
We can
This is
move
a
on.
nice problem. We can move on. And the second problem is from the last time we showed this condition. Do we need a poll for this one?
Yeah, I think author.
Author. Where's the author? Let's see who was here last time and who wasn't.
Almost everyone repeated.
Yeah. Everyone, James and Alex were here last time, but Evan wasn't.
Maybe I should text James.
Chris, people think you have proposed the second problem too. Do you guys see the results or no? Only
Yeah, we can see the results.
no.
I can, but not right now.
Yannick is winning.
Wait, where do you see results?
I don't know. The polls suddenly pop up on my screen.
Yeah, I see a poll and I don't see, like, I cannot click on it because I cannot vote.
Well,
I wonder why Yannick's winning.
You know the answer. Okay, let's end this poll.
I'm just saying. Yeah.
Yannick and Chris, top 2. Then David and Zooming, I think.
Yeah. Okay, it is Yannick's problem, right?
Yeah.
So why don't you go ahead and take a lead?
Sure. So just gonna first talk about how I came up with this problem. So first of all, this is I think if I remember correctly, EMC's extra math competition 2016. I think this was got strong number 22. Yeah, so I could just briefly talk about how I came up with this problem. So I think it's like similar to Chris, but like I guess like it was over winter break, and like it was like a few weeks before the competition, and we like need to finish up like the last few problems. I think we need like some hard algebra problems. So I just said to myself, let's come up with some hard algebra problems. Like I think I was like out eating dinner with like eating out somewhere, and so like I was just thinking, what is something that I can write down that looks extremely random? So I wrote down a plus b equals c times d. That looks extremely random, and it's like not even homogeneous. But like I like symmetric stuff, so I just said like, what if I require this to like apply for all permutations of a b c d? That looks very over constrained because there are 6 equations and there are only 4 integers. So and then I tried to work through it, and I figured out that it's actually a solution that's non-trivial. So that became the problem. So yeah,
when is the contest?
EMCC.
Yeah.
It's a
the full name is Exeter Math Club Contest.
Yeah, so it's like a math contest for middle school people, and like written by people in the Phillips Exeter Academy Math Club. Yeah, it's like
right. I mean, like when was it?
It was 2016. Yeah.
What? No, I mean, like, how close is it to winter break?
January.
That makes a lot of sense because I also was responsible. Carnegie Mellon's contest is in January, and if there's one thing I've learned about contests in January, it's that winter break is a very, very good time to write problems for math contests in January. Yeah. Okay. It's so many problems that were written in January.
Yeah. So
Yannick, I don't know how to solve this problem, but I can tell you I would start maybe to look at products, and I would look at something like A, B, C, D, write it into multiple ways. I don't know if it's helpful. Okay. C plus D. Let's just...
Yeah, go ahead.
A plus B. And then I can expand again, and I get AC plus AD plus BC plus BD, right? And this again, is it symmetric? Oh, yes, it is symmetric, right?
If you're symmetric, wait. Oh, that. Oh, I see.
Yep. Yes, because each variable is used twice. So because you get an A from the BC term and you get an A from the BD term. So that's 2 A's. And then all the other ones work. Okay. That gives you a pretty quick solution, I think.
You could write down other systems similar.
Right.
Instead of C plus D.
Well,
But you can Simon's favorite factoring trick what you've got right there.
But I think the most important thing is if you guess out one quadruple, you should prove this is all, right? That's much more challenging, right? Because there could be more than one answer.
Yeah.
Yeah,
right.
I guess
Just a side note from the contest writer's perspective, the problem implicitly asserts that there's a unique answer, but from the writer's perspective, we have to know that there's a unique answer. Otherwise, we might see two different answers that fit the conditions.
Well, I don't think you should even implicitly guess that way. It's only because in a contest, right?
Yeah.
If it's in any college or whatever contest, they give you this. You better tell people all the answers because who said it has to be unique?
Right.
I can easily change my comments to determine all 4 tuples, right?
Yep.
Yeah.
Yes, and they can be equal. They can be, if they're equal, all of them are 2 is fine, right? So.
Yeah, I mean the problem is that the answer not all equal. The numbers are not all equal. Yeah. So anyway, so I think Yvonne wrote down 3 things that are like products of two sums, and if you think about it, these three pairs all have the same product, and they all have the same sum. In fact.
You mean these?
Yeah, like C plus D and A plus B have like. Yeah, these 3 pairs, the C plus D and A plus B, A plus C and B plus B, D, and A plus D and B plus C, they all have the same product and they all have the same sum.
That's your key observation, right?
Yeah, I think that's like I think the first solution I'm gonna talk about, I guess.
Okay.
Yeah. So what does that mean for pairs of numbers to have the same sum and same product? So if you recall from Vieira's formula, it means that these 3 pairs are all solutions to the same quadratic.
Yes.
Minus sum
Sum
plus product, right?
Yeah. So in fact, if you think about them as unordered pairs, if you think about them as unordered pairs, then they are all the same unordered pairs. So let's think about what this means. Yeah.
Okay.
So let's look at first two pairs. So I think it's symmetric right now. So we can just assume that A plus B equals A plus C, and also B plus D equals C plus D.
Okay, Yannick, do you want me to write or you want to write?
Sure, I can also write. Let me share my. Let's make the whiteboard. Okay. So we have A plus D, B plus C. So let's look at the first 2 pairs. So let's assume, I guess without a lot of generality, that these 2 are equal, and these 2 are equal. So what this means is that B equal to C. So B equal to C, that's all good, and we can now look at say the second and third pair. So let's consider what will happen. There are again 2 cases. One case is A plus D equals A plus D, and then that gives us C equals to 2D. In this case, we must have A is different from everything else. Otherwise, if these are equal, then we have A equals B to B. Then
no matter what, 3 of them must be equal to each other.
Yeah.
Right?
So in fact, 3 of them must be the same, and the 4th one must be different. So in any case, we have the general form that like the answer must be of the form U U U V, and we basically have 2 equations. The sum of the 2 of them equal to UV, and we also have U plus V equal to U squared. So the first one gives you 2U equal to UV, and also so this gives you u equal to 0 or v equal to 2. Well, what happens if u equals 0? If u equals 0, then we have the second equation is v equal to 0. That's not good. And if v equals 2, we have u plus 2 equal to u squared. And we have u equal to 2 or negative 1. And of course, we don't want everything to be the same, so we discard 2. So basically, we have the final answer is negative 1, negative 1, negative 1, 2. Yeah, I think there are easier ways to make the same observation. So let me see if we can just erase the whole thing. So if we just write down two of the equations, then what we have is that if we look at these two, we see that they're just A, B, and C swapped. So we can just subtract the two. This gives us B minus C equal to C minus B times D. So either B equal to C or D equal to negative 1. Yeah. So, but
or both.
Or both, but yeah. Basically, my point is that based on the problem condition, not all of them are equal, so we can just assume that B and C are not equal. So B not equal to C gives us that D equals to negative 1. And also by the same token, A equal to negative 1. And I think the whole problem falls apart from there as well. So that's another way to approach the problem. I think, yeah, so I guess when I proposed the problem, I came up with the first solution, which I think is quite nice. But like in the actual context, it falls apart more easily. I think more teams got this problem than I expected. But but like there are still some things in the first problem that in the first solutions that I still want to pursue. So you can think about how to like generalize this problem, and who knows.
Yeah, you can't be scared by all those 6 equations, right? Mm-hmm. You have to pick the useful ones, like the one you picked right now, or you pick the earlier. I think the earlier method really have some essence into it. Maybe you can expand much more because that discriminant and the root argument is very cool, right?
Yeah, so it really depends on what the first two equations you picked. So if you pick so this is one way of picking two equations, and this is the other way of picking two equations, and these two leads you to different observations. Mm-hmm. Yeah.
So I guess if you want to keep the symmetry, you go for polynomials. They have symmetric sums when we write their roots from Vieta. Otherwise, you have to break the symmetry, so you pick non-symmetric ones.
Yeah. So again, my challenge to the viewers is: can you think of something more interesting with this problem? Like, yeah, we'll see. Okay, I will stop here.
I wouldn't be surprised if, in retrospect, if it was a team problem, like maybe some teams got it by guessing. They might have reasoned, well, they can't be that large in absolute value, so just playing with numbers, maybe.
Yeah. I think I forgot what was the reason, but like originally when I proposed it, I like asked for real numbers. I think later on we changed it to integers to make it less obvious that it's an algebra problem. But yeah.
So we go to the next one?
Sure. Do we want a poll for this one?
Sure.
Okay, so what? Competition or the proposer?
Competition.
Competition.
Why not just do the Cartesian product?
Oh no. Does Zoom allow that many?
Wait, guys. I'm not that. Okay, stop sharing. I'm not that fast. Let's see where it was proposed. Okay, we need to show the problem too. We need to, guys, for you to see.
We're seeing it, right?
I can see it.
Yeah, I can see it.
So we have a square PQRS that lies in the first quadrant, okay, and points 3, 0, 5, 0, 7, 0, and 13, 0 lie on lines SP, RQ, PQ, SR. So on some lines that go through the vertices of the square, right? Through the sides of the square. Yeah. What is the sum of the coordinates of the center of the square PQRS? So pretty much we probably want to have a good drawing. And yeah, okay. Here's the pole. Armo 1.
Armo is the origin, but actually it's not. It's AMC, right?
It is AMC, 2012.
If it were ARML, the square would have been ARML.
Yeah.
Good point.
Well, we could change the problem, you know?
Yeah, that's true too. Yeah.
Okay.
That would have been too easy, I suppose.
Yeah, we change the ARML and then ask them.
Yeah.
On a different test.
Or make it AIME and it's really an ARML problem.
Yeah. Okay. So I wrote this for little, coordinates geometry because you always want to find some kind of coordinate geometry. It's not that, it's easy, but it's still not that completely trivial, right? So the first thing is in the beginning, students have a tough time to even draw this diagram. They were confused what's going on with these 4 points, right? But you think about this way, you basically have a square. Those are the 4 sides of the square. If the square is laid out nicely with its sides equal to parallel to the axis, then you will not have 4 points, right? You will not have 4 intersections, right? So that means the square must be tilted, right? And then immediately you will have 4 intersection points because none of the sides will be parallel to the x-axis anymore. Then you will have 4. So that's one little step you have to think a little bit, right? So Ivan, can you push the paper up so let them see the picture? Yeah. So you know so this is the picture, right? Right? When I teach class, just people talking about the math problems or whatever, I always heard people say this: "Let's bash it." So I always want to ask them, "Do you know how to bash?" I give you a problem for you to bash, right? It is coordinates because you guys don't like geometry, you want to bash. So I give you a problem clearly setting up for you to bash. How do you bash it, right? So this again, if you don't do it well, you will take lots of time, right? So the thing is, if you really want to bash, you still want to know very important thing, because bash involving variables. So what should be the variable here? Is technically you want to know what's the slope of this line. Because if you know the slope of one line, you basically know the slope of everything, right? So yeah, so that's why you should use one of the angles to be maybe one of your parameter. That might be easier. Because then you immediately know what is this tangent is, right? So let's say one of the small angle here is a theta. No, the small angle. Use the small angle is better maybe. It doesn't matter. That one is fine too. Yeah. No, what I mean is the smallest angle. Yeah, use that one might be the easiest. Just say that's theta. And the only thing we know it's a square, right? So we have to use this side length to decide our what? Our equations, right? So we know this is 6, this is 2, this is 2. And how do we represent the sides? Yeah. That's 2 cosine theta also. And this one, This one you can draw this thing. You can draw this line, right? You can draw the line from 7, 0. Or yeah, because you want to use 6, right? So the easiest one is go draw a line from 7, 0, right? 7, 0. Right. Are you guys hearing me or you cannot hear me? I cannot hear everyone. Ivan, can you hear me? Can you say something?
Yeah, you're okay.
Yep.
Yeah. So then you have the equation, right? You know what sine theta or tangent theta is.
So 2 cosine theta is equal to 6 sine theta, right?
Yeah.
Okay, so tangent of theta is equal to 1/3.
Yeah. Right? Okay. Now at this point you know everything, right? Because you know the slope of the line now. But what is the easiest way to find this point? It's not about finding those 4 points, right? How do you really bash it well?
You probably could look at like the triangle formed by, so you have, this is sort of just like a wave in the dark, but you have like you have the points 4, 0, which is the midpoint of 3, 0, 5, 0.
That point.
And then that gives you an intermediate triangle that you can probably work with.
Yes. And you want those 2 lines, right? Because those 2 lines you know clearly their intercepts, which is 4, 0 and what?
10, 0.
10, 0. And then you have the line equation. And then you can bash it, right? So still, you know, when you're solving coordinates, you still have to do it kind of like a little bit carefully rather than just getting lots of numbers and maybe have mistakes.
This is like a coordinates problem that's not really a coordinates problem in some sense. It's like it's a coordinates problem that still like I don't want to say succumbs, but like still yields itself to very synthetic ideas. Because in this case you still have all you need is like to compute the the length of the altitude, which you can do purely synthetically, because you know that
I see that's 3, not 1/3. That slope is 3, is it?
Yeah, that line looks steep. Yeah.
Or you could do that.
Yeah, that line looks steep.
And this is y minus 0. This will be negative 1/3.
Negative 1/3.
Yeah.
10. Yeah.
So we can stop here, right? So we can go to the next one.
Okay.
Because the next one is quite hard. We need more time to talk about it.
Okay, let's read it first. Yannick, maybe you can read it for us.
Okay. So at a university dinner, there are 2017 mathematicians, I wonder which year it is, who each order 2 distinct entrees, with no 2 mathematicians ordering the same pair of entrees. The cost of each entree is equal to the number of mathematicians who ordered it, and the university pays for each mathematician's less expensive entree. I guess I want to save money. Yeah.
Overall, all universities are cheap, you know?
Yeah.
Even though they have all the endowments, they still want more money, you know?
Yeah. Yeah, of course. Over all possible sets of orders, what is the maximum total amount of the university could have paid? So I guess the mathematician wants to rip the university off, even though, okay.
They all live on funding, so they want to save money, right?
Yeah, it makes sense.
Okay. Yannick, did you see this problem when you were?
I saw this problem, but like I never like seriously thought about it. I heard it's really hard, and I mean, I gave it a thought about it like a few minutes before the show, and it doesn't look nice.
Okay. Well, I know James has something to say about it, but James is not in the audience. Maybe we will ask Evan to help us think of this problem in a good way. Evan, are you here?
Yep. All right, let me set up my projector. All right. Okay, hopefully that works. What is this here? Don't need that there. Okay, so this is a problem from USA TST. The year is not actually 2017. It's the December 2017 TST. So it was for the 2018 team, but it appeared in 2017. So let me first start by setting up the right language, which is like the very hard problem from last time. This is actually a graph theory problem, but it's not a graph. Most of the time you're used to when you have a graph theory problem, the vertices are the people. In this one, you actually want to think of the mathematicians as the edges. And the entrees as the vertices.
Yeah.
That's not how you spell vertices. Vertices.
Evan, this problem keep me very entertained during the proctoring, you know, those long 4.5 hours.
Yeah. It's I think there was only one. There was 1-7, if my memory serves me. I think it's.
And I think who know,
Yeah.
we know the person who got that 7.
Yeah, but there's a bit of a backstory. So, if more people order a dish, then shouldn't it be cheaper? No, if you're a restaurant, so someone asked in the Q&A, what if more people order a dish, shouldn't it be cheaper? And the answer is, if you're a restaurant and the demand is already fixed, you adjust the prices to maximize your profit.
This
So
is
everyone's just
almost
trying
like
to maximize.
HMMT scoring, you know?
Okay.
Well, it isn't the less soft the more score, but
So in the graph theory notation, you have like some sort of graph. You have a graph G, and the quantity you're trying to maximize in this notation is for every mathematician. You take the edge. You take an edge VW of the graph, and then you're looking at the 2 degrees of the vertices, so the number of people that ordered that entree. And the university is paying for the smaller of these 2 things. So what you're looking at is the sum over the edges of the min of the degree of V and the degree of W. So yeah, in graph theoretic terms, that's what's happening. So the first question is like, okay, well, what kind of graph do I want if I want to try to minimize this quantity? And intuitively, if you're, if you're trying to bankrupt the university, what you want to do is you want to like try to get a bunch of vertices of very high degree. Like you consolidate the mathematicians as much as possible so that they're all ordering the same thing and driving up all the prices. So, well, what's the most tight graph there is? The most tight graph would be the complete graph. Okay, and where you have some entrees and you take all the pairs of things between them. But unfortunately, you can't quite do this for this problem because, well, in this problem, 2016 is not a triangular, or 2017 is not a triangular number. The number of edges in a complete graph is always something choose 2, but it's almost a triangular number. It's 1 more than, I think it's, I'm going to get this wrong, 64 choose 2, right? So intuitively, the graph that I want is I'm going to take, well, we're going to try to take these 64 guys and take a clique on 64 vertices. So I have 64 entrees, and then I get 2016 mathematicians this way. Oh shit, that's not K64. Okay, let me just write K64. And then I have 1 person left over. I don't really know what to do with it. So I'm just going to go and like put them off onto this side here. And it turns out that this is actually the correct answer. Correct construction. All right, construct construction. And if you compute the numbers, you'll get some number. I think it's 127009, but it doesn't really matter what the number is, but oh no. I need to hide that thing. It doesn't really matter what the numbers are. That's just, I want to show that this particular graph is best optimal. Now, as people have been saying, the proof that this is the optimal graph will actually take me like probably the rest of this session and a good chunk out of tomorrow's session if I want to properly do all the details. It's very hard to do it in the time limit for that matter. Oh, also James is here, so if someone wants to add him, he can like argue with me.
Is James here?
Yes.
James, how's the NFL draft? Did they draft the person you want?
James is not in yet.
Yeah, it might take him a few moments to show up.
James,
I see his face. Yeah.
You should unmute yourself.
Oh, I'm watching the draft right now, so it's okay.
He's still watching the NFL draft. All right. Okay, so I'm not going to try to do a complete solution on the video because it's not going to make any sense. I will very briefly try to tell you what the general idea is and then move on to the part which I want to talk about, which is the story of how this problem came up. So the idea of solution, all right, scroll up. I'll save the main equation here. So this is some
Avan, if it's a complete graph, is solution much easier?
Is the solution much easier? It's a lot easier, although it's still an Olympiad level problem. I think there's a few for the complete graph. I think there's like a couple ways that you can simplify things a lot, but
so maybe our students, if they want to have a challenge, they try this problem for a complete graph first, right?
Yeah. Anyways, let me say the idea of the solution, which is that, as I said, the intuition is if you want to bankrupt the university, you want to consolidate the orders as much as possible. So to this end, let's suppose there are two people, V and W, who don't share an entree. So this edge is not present. Sorry, what am I saying? There's two entrees which are not ordered like so. So you have entree V, entree W, and no mathematician orders V and W. No, actually, sorry, I don't want to do this way. Back up. Let's just take the entree which is ordered by the fewest people. So this is the entree ordered by fewest people.
Mm-hmm.
Well, as I said, since I want to consolidate all the orders, I don't really like this. So this entree is, there's some edges going out here, and then there's this big giant graph out here. And my idea is, okay, well, if I want to bankrupt the university, what I want to do is I want to take out this vertex altogether, but then I have these three edges dangling off, or however many is in your actual example. And what I can try to do is I can just stick these edges anywhere else in the graph. So take them, you hold one endpoint the same, and then you stick them like wherever you can find space for them. So something like that. So if you can delete the smallest degree and rewire, then you're happy because the university is now paying more money. There are some obstructions to this because sometimes your graph will be so tight that you run out of space when you do the rewiring operation. But the basic premise is you can show that unless G has way too few vertices, so I'll just say very few vertices. Unless G has very few vertices,
Evan, I can't see your screen. You have to push it up a little more. Yeah.
So if G has very few vertices or has a universal vertex. So a universal vertex is a vertex that's adjacent to everyone. So if you have a universal vertex, you're kind of stuck because when you delete the bad vertex here, there's literally nowhere to go because the universal vertex is already adjacent to everyone. But unless you're in certain edge cases or you have a universal vertex, this operation is possible. So the main case you have to deal with is if I have a universal vertex, so I have a vertex that touches everyone. And that brings to the second idea, which is if universal vertex exists, you can delete it and induct. Because what will happen is if I have a universal vertex and I destroy it, I know exactly what will happen. Every other entree will have the price decreased by exactly 1, and the total value of the edges I deleted is exactly equal to the sum of the stuff that's below it. So if you have a universal vertex, I have enough of an understanding of how the item behaves that when I delete it, I can do an induction downwards. So that's very briefly the idea behind how you solve the problem. So for the rest of the time, I want to talk a little bit about the backstory behind this problem. So the backstory behind the problem is that sometime around the end of 2016, towards the end of 2016, I was working on a different problem. And that problem was from the APMO, let's see, 1989? Let's find it. So in 1999, there was a problem on the APMO that asked you if I had just have a random graph with so many vertices and m edges, show that it has at least this many triangles. And the intended solution to this problem is that what you do is you try to double count it in the following way. For the number of triangles will be equal to 1/3 times the sum over edges of the number of edges, number of triangles which use that edge E. So this is actually an equality, and it's a kind of a standard thing you might do if you're trying to double count the number of triangles. And what the APMO problem does is it's like, okay, well, if I have V and W, and I want to bound the number of triangles that use V and W, one thing you can do is you can say, let's just look at degree V plus degree W minus the number of vertices. So each of these edges, degree V was W minus N. Let me double check that's right. Something feels off there. Oh, sorry, this is a lower bound. You're just like, okay, every guy sticking out of V and W creates at most one triangle. Some of them might overlap, but I mean, if degree in V or W are both really big, this will be a bound that works for the APMO problem. This was not the thing I tried. I did not solve the APMO problem because the way I bounded it instead was to try to take the smaller of the degrees. I'm like, well, if I have a vertex of degree 3 and a vertex of degree 5 that are adjacent, for example, there should certainly be in at most 3 triangles because it's determined by just which of the edges at V I pick. So one of them works and the other doesn't work, but it's how I came up with the TST problem. And it was December of 2006. It was very late in 2016. So I was like, okay, that's great. Let's try to solve this problem. And I couldn't solve it in general, but I was able to solve it for a complete graph. So I had a solution that worked for 2016 vertices.
Which is good, great, because that is the triangle number, right?
Yeah, I'm like, oh, this is really great. I can do it for any triangular number. The issue was that it was late 2016. So I was like, well, I'm not going to get this onto any contest in time. And so I kind of forgot about it for a while. And then a few months later in 2017, I was like, okay, I couldn't do it for 2016, but maybe I can do it for 2017 and then try to rush to get it onto the team selection test. And that is exactly what happened. So that's how that problem actually ended up there. I remember I was, I don't know, I was somewhere bored. I was like at a physical workshop watching someone put together like a wire project or something, and they wanted me to keep them company because it was late at night. So during that time, that's when I came up with the solution to this problem. And I got it on the TST in 2017. But the story goes on where someone else saw this problem and was like, oh, that looks interesting. And so a couple of undergrads whose names you might know, Mehtab Sani, Ashwin Sa, and let me make sure I get this right.
Oh, they wrote a paper, and MIT even have an article for them, right?
Yeah, they wrote a lot of papers. Yeah, this one was just Ashwin and Mehtab. Started where like, okay, well, this problem, the author solved it for 2016 and 2017. Why don't we try to solve it for all values of n? And that is exactly what they did. And that result ended up becoming a paper. And I'll show you where the paper is. The paper is called On the Discrepancy Between Two Zagreb Indices, and it's, this is the main quantity. And they actually managed to solve it for all n. The TST problem only asked you for 2017, but they're actually able to figure out for every n what the best construction is. And the answer is kind of surprising. It's like, I'll go into the PDF. So there's the university dinner problem at the start.
Yeah, Evan, can you post the link in the chat too?
Can I post a link in the chat? Yes.
Well, I think they can search their name, Ashwin Sa. It's easy to find.
There are more
I'll
papers
post
than
it anyways. It doesn't really matter. But yeah, this is where the paper is.
Yeah.
And the solution relies heavily on 2017 is 64 choose 2 plus 1. But then they managed to get it for any graph. And the result is something absurd. It's like, you take the smallest triangular number that's below the thing you want to say. And then it breaks into 3 cases based on how far you are off from the triangular number that's below you. If you're very close, it's the thing that we were trying to do in the TST problem. If it's between 2/5 and 1/2, then you have to do something different. And in the last case, it goes back to the sort of thing that looks like what we did in the TST problem, where it's not quite. It's like you take a complete graph and then delete some edges that don't touch each other. So they actually managed to do this, and they got this 20-page paper out of it as a result. There's a lot of combo. I haven't read this paper yet, so I don't know exactly what it does. So yeah, that's the story of this TST problem that ended up in someone's paper because they replaced 2017 with n.
That's very good. So actually, your solution is very relying on you only have one more, so your adjustment is easier than their paper is, right?
Yeah, mine is quite specific to that. Because what happens is in my solution, when I'm doing this induction, what happens is after the first induction step, when you look at the equality case, why isn't it showing up? Today. Okay, whatever. When you do the induction, what happens is when you have in the correct answer, which is the K64 with an edge sticking off it. This is okay. So we have a universal vertex, and then there's the 65th vertex sticking off. And as I said, the idea behind the solution is once I have a universal vertex, I can delete it and control everything. And what happens is after the first deletion, you end up with K63. So once you have the K63, then you can keep going. So when you solve the 2017 version of the problem, you actually need to solve the 2016 version as well in order to get the solution to work. But it works because after your first induction step, you're in the easier complete graph case. But in general, that's not what happens. And even for small numbers, if you take, this is one thing of the problem that really drove people nuts, is if you take 3 choose 2 plus 1 equals 4, you would hope that the answer would be a triangle with an edge sticking off. That would be what's consistent with the TST problem. But it's actually not. If you look at this graph, the prices that you get are, this guy's worth 1, 3, 2, 2. So you end up paying, how much does university pay? 7. Yep. But if you take a cycle on 4 vertices.
Oh no.
it's actually every guy's worth 2. So you can make the university pay slightly more. You can make them pay 8. And the reason why this is happening is because when you try to apply the argument I said, which is you take a smallest vertex, delete it, and rewire, you literally run out of space. Like you have these 2 edges and you want to stick them in place, but the triangle only has 1 empty slot left. Mm-hmm. So even for like the smallest case, you can already see that something is not going to be very clean. There's going to be a little bit of fight you have to put up. And 2017 is big enough that, okay, that 65th vertex just dies right away and you're okay. But once you start adding more edges, you start seeing more and more behavior that looks like this. Yeah. So incidentally, for grading, this counterexample was extremely useful. You could figure out when people messed up by testing their proof against this particular counterexample.
James, you want to talk about how you solve this problem?
I don't actually remember my solution that well, but I consider this problem to be like a C7 or something on the IMO shortlist. What I did is I just made everything like an algebraic expression and smoothed a bunch of algebraic variables together, so it turned into like an A3. So that's how I did it. I don't remember the details. I think Evan typed up my solution somewhere.
I actually typed up your solution, yeah.
Yeah. So basically, like I think everyone else tried combinatorics and didn't solve it. So I got lucky because I was just like, I can't do combo, so I'll just do algebra.
This is the right mentality. Take every combo problem and turn it into something that's not combo.
Yeah. Also, like I think it was just hard for people because I think the first 2 problems on the TST were really hard for people.
Yeah, that was.
I got lucky because I like had like over 4 hours to spend on this problem, so it's good.
Wait, what?
Yeah.
Yeah, actually, which year? That was the year that the average score, the median score on that test was like 2, right?
2 points?
Yeah, that I remember. This was a test where the median score was 2 on the first day.
Oh, wait, really?
Yeah, it was really hard.
I don't think it was that low. Oh. I got lucky though, so that's good. This is why I made IMO that year.
Yeah, you need all those points to make it.
Hey. I also finished this test with like 2.5 hours left, okay?
Oh, wow, that's really fast. Yeah.
Such flex.
Yeah, I feel like this problem is like really details oriented. It's like, I think the idea that I think none of the ideas I said in the combo solution are like surprising to anyone, I would say. It's like if I tell you the idea is you consolidate the graph and then once you have a universal vertex, you delete it. Those I think are really natural ideas for this problem. But the execution is really, really finicky. And it's because
I can think of this like very hard to formalize. Yeah.
It's very hard to formalize, yeah. You have to work very carefully to make sure you don't mess up.
I don't think I know the combinatorial solutions though, like fully.
Well, you should have came earlier. Oh, no, you were watching.
Yeah.
Kind of.
You should explain us your solution someday about all those algebra.
It's not very insightful. There's nothing worth like doing.
No, I think if you want to translate every algebra combo into expression, is the hardest part of combo, right? Actually.
Like it was like everything was pretty natural, I think. To do.
Yeah. I would say this is a problem that requires care rather than a trick. But it's very largely about being careful.
And being careful is difficult to do under a time limit.
With 2 other problems that kill everyone.
Okay, that's very good. We are 9 o'clock and we should end up here so James can watch his TV and the rest of us can get some rest, right?
Yep.
So everyone, good night.
Good night.